In today's video, we'll learn how to differentiate using the power rule without the need for the chain rule. Furthermore, by utilizing this method, we'll be able to integrate more quickly without the need for substitution in future lessons. This is the equation we'll be learning today. When you differentiate a box with the exponent n on the left side, the exponent n moves to the front while decreasing by 1, resulting in an exponent of n minus 1. The term that needs to be multiplied at the end is the derivative of the box, denoted as box prime. Always remember that the box prime is a term that must be multiplied whenever we differentiate. Similarly, when integrating, the first term you should look for is box prime. I will explain this further later on. Let's now differentiate our first example, y equals x squared. To find dy over dx, let's apply the formula mentioned earlier. Comparing it to our problem, we can see that x will be inside the box on the left side, and the exponent n will be 2. So on the right side, instead of n, we substitute 2. Inside the box, we write x, and for the exponent of the box, we put 2 minus 1. Are we done? Not quite. Well, we still have the box prime remaining. Differentiating x inside the box with respect to x gives us 1. Therefore, we substitute 1 into the box prime. As a result, our answer is 2x. You might wonder why we go through the trouble of introducing box prime and multiplying it by an unnecessary 1. There are two reasons for this. Firstly, if we continue to multiply by box prime as we've done, you will easily understand implicit differentiation, a topic you will encounter later, without any additional difficulty. Secondly, integration becomes significantly easier. It becomes so straightforward that you can find the answer mentally. If you are curious about these two aspects, click on the link top right corner to watch the related video. Now let's look at second example. We have y equals x squared minus 2x to the power 4, and to find dy over dx, we'll once again apply the formula shown above. Just as we saw in the previous problem, we can see that x squared minus 2x will be inside the box on the left side, and the exponent of the box will be 4. In the differentiated result on the right side, the exponent, which was 4, moves to the front and becomes 4. Inside the box, we still have x squared minus 2x, and the exponent of the box decreases by 1, becoming 4 minus 1. Now, for the final given box prime, we substitute the differentiated term of the previous box, which is 2x minus 2. Therefore, the answer is 4 times x squared minus 2x to the power of 3 times 2x minus 2. In fact, if you master this method, you'll be able to solve all differentiation problems in just a few lines. Now, let's delve a bit deeper into the advantage of the quick integration when multiplying by box prime as mentioned earlier. Shall we differentiate box to the power of n plus 1 over n plus 1 that we see here? The exponent of the box, n plus 1, moves to the front, and subtracting 1 from the exponent gives us n plus 1 minus 1. Moreover, we must multiply by box prime, and the term n plus 1 in the denominator of the left-hand side is a constant. So we write it directly in the denominator on the right-hand side. So when we simplify this expression, it becomes box to the power of n times box prime. To reiterate, the fact that differentiation of box to the power of n plus 1 over n plus 1 yields box to the power of n times box prime implies that if we integrate the right-hand side, the left-hand side should be the result. Therefore, the integral of box to the power of n times box prime is box to the power of n plus 1 over n plus 1 plus c. Here, c represents an arbitrary constant of integration. Let's bring back the problem and answer we solved earlier. We differentiated x squared minus 2x to the power of 4 on the left side and obtained the result 4 times x squared minus 2x to the power of 3 times 2x minus 2. So it's only natural that integrating the right-hand side should yield the left-hand side. Let's use the integration formula mentioned earlier for verification. Taking out the constant 4 from the integral and writing down the integral x squared minus 2x to the power of 3 times 2x minus 2 dx, we can compare it with the integration formula above. We can see that the box contains x squared minus 2x, and it's 3, and box prime contains 2x minus 2. Now let's put the same term as the left box, x squared minus 2x, into the right box, and substitute 3 for the exponent and denominator n. Finally, let's add the integration constant c. When you simplify the expression, we get x squared minus 2x to the power of 4 plus c, And if we exclude c, the original equation is reproduced. We have just performed integration quickly using the green color box prime without substitution. Understanding the existence of box prime in differentiation and being able to identify box prime during integration make integration remarkably easier. Now, let's differentiate y equals 4 over square root 1 minus 2x. By expressing the denominator as a negative exponent, it becomes 4 times 1 minus 2x to the power of negative half. To differentiate it, let's apply the formula. Since the problem has a multiplication of 4 in the front, let's also multiply by 4 to start. We put 1 minus 2x into the left box, and the exponent value n becomes negative half. On the right side, it becomes 4 times negative half, and the box contains the same term as the left side, which is 1 minus 2x. The exponent of the box becomes negative half minus 1, and finally, for the most important box prime, we substitute the derivative value of 1 minus 2x, which is minus 2. Simplifying the expression, we get minus 2 times 1 minus 2x to the power of negative 3 over 2 times minus 2. And upon further simplification, it becomes 4 times 1 minus 2x to the power of negative 3 over 2. That's the answer. Now, let's differentiate y equals sine x plus cosine x to the power of 3. First, let's bring out our box rule formula and compare it with the problem. We can see that the box should contain sine x plus cosine x, and the exponent value n is 3. Let's fill in the right box and the value of n. The n becomes 3, and we put sine x plus cosine x into the box, while the exponent decreases by 1 to become 3 minus 1. And the most important part is the box prime, which requires multiplication. The derivative of sine x is cosine x, and the derivative of cosine x is negative sine x. If you are not familiar with this yet, don't worry at all. I'm currently preparing videos on differentiation using the box rule for trigonometric functions, exponential functions, logarithmic functions, and more. So for the box prime, we substitute the derivative term of sine x plus cosine x, which is cosine x minus sine x. Summarizing again, we have dy over dx equals 3 times sine x plus cosine x to the power of 2 times cosine x minus sine x. I apologize for mentioning integration, even though today's video is about differentiation, but it keeps appearing, so let me briefly talk about integration once more. Let's bring back the integration formula introduced earlier. Now let's integrate 3 times sine x plus cosine x to the power of 2 times cosine x minus sine x right above. We put sine x plus cosine x into the box and set the exponent n to 2. And for the green box prime, we put cosine x minus sine x. Now, we only need to fill in the right box. We multiply 3 and put sine x plus cosine x into the box and set n to 2. The exponent and the denominator of the box becomes 2 plus 1. Finally, we add the integration constant c. Simplifying the expression, we have 3 times sine x plus cosine x to the power of 3 over 3 plus c. And upon further simplification, it becomes sine x plus cosine x to the power of 3 plus c. As you can see, it is exactly the same as the original function we differentiated. The reason I keep explaining differentiation and showing integration is to demonstrate how crucial the green box prime, which we multiply at the end in differentiation, plays a significant role in integration. Integration is simply the reverse process of differentiation. If you can separate the box prime in integration, it becomes much easier to integrate. To achieve that, it is necessary to be aware of the existence of the box prime in differentiation and maintain the habit of multiplying it at the end. If there are any parts that you don't understand or if my explanations are insufficient, please let me know in the comments. I also plan to create more videos on differentiation for various functions. I appreciate your continued interest and support. If this video has been helpful to you, please like and subscribe. Thank you to all of you who have watched it until now. I'm your math guardian, Alex.